本当は意識する割に自分が。
Something like square root of square root of theta. So I think
いや、結局は入ってた方がないですよ。ディテールはやっぱりなんかわからない。いや、どうしようもない。根本的にこのちゃんとアニメーションでできるって言ったんだったらそれがいいことです。東にブログ。
別の経験とか20年以上の
北京でいう師匠さんですけど、友達がいるに、感じるんですよ。
Then the rotation number shows this on cost. Can be more of
っていうのは、まあ、その解析のために必要だっていうのはそうかもしれない。解析を中にあるために、そういう得られない。
That's interesting. Say
さっき言ったようにアングルも決めない。例えばそういう本当に柔らかいことではないので、ちゃんと一歩でテレビとか使うやっぱりあれしまない。その状況を保ったままパターンをするんじゃなくて、その多分決めじゃないして。よし、これには。
僕なりリンク聞かれてないんですけど、本人から聞かせてね。また劇ですね。
いや、あったらいいけど。会うことも少ないから。あんまり長い。
リンクスケジュール使ったんですけど、まだ書いてるだけなんですけど、何か、この日にこの人の話聞きたいとか言いますか？
モーリックさんね、私たち聞いてないなと思ったので、これは。
多分、この筆典系の話は最近やってないですね。
ああ、そうなんですね。じゃあ、
読んでるですけど。
はあはあ。それ。いいか。
山田だけじゃなくて、まだ適当に作ってた。
様子ができるんです
様子が。
いや、そう、中日とかやる。中日人来ない。
まあ、海外行くか来る人は時差ボケとかで後にした方がいいのかな。
そう。日本中で、人は少ないと思って。ちょっと興味見ました。
はい。
Feedback today is Todor Milanov. He's going to talk on Genus-0 permutation-equivariant KGW invariant of the point.
First, see what is KGW. KGW means K theoretic boundary. So in the first part of the talk, I want to explain construction in theoretic form space. This construction due to ancient and basically the main motivation was to find a K theoretic version of the result of the Milanov-Todor that realizes the homology of the Hilbert scheme of points on the surface of the thin space. And the K theoretic version, which turns out to be much simpler than. And actually, the idea to incorporate this into K theoretic concrete theory came to me 1 year ago. They were talked here. I think he talked about some verification of this construction. Yeah. So what is this construction? So suppose that you have a finite group. First, we want to recall what is an induced vector bound. So suppose that you have a finite group, G, H is a subgroup, and X is a G space. Logical. Then let also find. So E is going to be an H equivariant vector bound. Then the induced vector bound, this is a construction that allows you to promote this to a G equivariant. This is done. So set theoretically, this is the way. So we consider the set of all maps G3, the total spatial vector bound, such that they satisfy the following two conditions. And first, N is H equivariant. And the second condition is from position by that is G equivariant. And now this is a nice exercise. If you want to check the dense neutral structure of a smooth bound, the vector bound will set, and also the natural action that the action will include this into a G equivariant. Vector bound. And if your space is a point, this is the well-known construction of induced representation theory of finite. And also, let me say that the rank of this vector bundle is the rank of E times the index of the group, the subgroup H. Now, this K theoretic for space is defined in the following way. So the right sum over O and 0 infinity. And we take it's an invariant K of X here. Here, this is the symmetric group thing on this here, mutation. On this vector space is naturally a graded permuted algebra. When the property is defined as follows, we take two invariant vector bundles. One is SN invariant, and the other is SN invariant. Then you simply take a dual vector bundle. So then these are basic CFL. And an example, actually, I want to use some interpretation in this example later on. If X is a point, X is a point, then let us define virtual representation of the equivalent in this case is representation. So this is a virtual representation with character. This is the trace of G. This representation. So it is one, it is N. If G is a cyclic representation. And it's 0 on the way. And then for the information can be testing, it's easy to see it. And the top space in the face close to the polynomial. Okay. So it's a representation. Yeah, so for any set, because it's modulus. So now a similar result actually so jump two for the general maybe that makes something more maybe we assume from that one that this is objective. Working with work to assume that KY actually. Let me fix also a basis. Okay. So another this is a topological K-ring, and I want to work with complex coefficients. So general pairing is defined by the rotating primal. So X. We define so Let me denote with phi up right, phi upper A for each. The closed way. In other words, with respect to the it's PATB equal to delta A. We need to find the following elements in the discrete space. So we know them in QRA. So we take stereo tensor product of P over A. Then I tensor with PR. Just take this neutral vector space and into it trivial SM invariant vector bundle. Yeah. So this becomes an element of SR invariant KV. And then the result of trade chain function. These elements are polynomial generated. Think of it space. Just formula for A, where A is greater than 1. Don't make sense. What the diamond is back. Yes. And no, what is interesting is that also the derivatives they have a k-to-electric interpretation. Indeed, so this derivative is defined like so Sn then to Sn minus 1. This is this involved. This derivative, so the formula for the derivative is following. So if you take some Sn equivariant vector bundle of Xn, then let me write the formula, then I will explain it. You take some trace. And there is a push forward. And there is a push forward vector bundle. K is still tangent product yarn. It's Sn vector below yarn. In stereo product, the trivial vector bundle stereo product n minus 3. Then tensor, we take the restriction. So we simply think of E as SR is Sn minus 9 variant vector. And this projection we have to think of Xn as x to the r times x to the n minus r, and then you project n minus r. And now when you compute this push forward you're computing some shift topology in this yard. So when you compute the push forward, you obtain some virtual vector bundles, Sn minus R invariant vector bundle N minus R, whose coefficients are representations of SR. And then we take the trace with respect to this. So we will obtain. And this formula actually is very convenient because in complex geometry there is so-called Lefschetz trace formula. So there is a way to compute these traces using. Okay. And so this is the instruction. Okay, so how do we define permutation equivariant KGW? So let's consider the following diagram. So this is the modular space of stable length. Genus, so this is maybe you can think of some energy, which is linked to the brain. And then there is some mark points. Somehow we want to split the mark points into two kinds. The first in and the last game. So there is an evaluation at the first n mark points I will denote it with lower indexing. This goes to text here. And then there is an evaluation method at the last k mark point. So I will denote it with upper index k. The evaluation method goes back to the k. And here I want to remember the actions of the symmetric group. Okay. And then the invariants I'll denote them for a later rotation. So P A1 L to the K1. Different on the variable. So this it's not going to be a number, it's going to take values in this case already. Space. Sufficiently long band necessary and no way. It's not necessary at all, just that I think this would be really it's not that. So the invariants are defined in the, so we take sum over all possible k from m to infinity. We sum over all possible these. And then we do the following. So we push forward. Full vector. In one. 1 to the K1. And then we're going to look at this. So we get here also the virtual structure. Then and also we didn't say T here means the creation. The image of this curve has some degree. Also, we didn't say what L1 and Ln are. So for each point in the modular space, you can look at the cotangent line at the ith marked point. In this way, you get some line bundles. Some say this is this coefficient here is S K S to the K, which is into space, but the entire correlator, since this is an infinite sum, it belongs to the completion of this space. So the completion of
So is it a perfect complex of length 2?
yeah. This is a coherent sheaf on the modular space. Yeah, but you can think of it. Right. This is not the YP. So what do you do with this? Of course, the goal is can we compute these kind of structures? Okay. Well, so let me introduce first the following. So somehow the genus-0 2-point and 3-point correlator play an important role. So namely, using the 2-point correlators, we define a metric, linear form. Here we have the point correlator. We can define also this form S metric. So it's going to be an element of endomorphisms of the K. You can think these are n by n matrices, whose entries are going to be formal power series in the negative variables. Formal power series is the equivariant permutation, equivariant parameters, and the coefficients would be rational functions in some auxiliary parameters. So that's the shape of this. Is defined by this equation. So you take the pair in S of mu q, apply it to phi A, the pair into P, and this is going to be A. And this is A divided by 1 minus 2 inverse L And also we define K theoretic the usual way. Yeah, is defined in such a way that very is C is just a 3-point correlation. And then we have the following from so the first property is that if you take a derivative with respect to Q1 A, somehow mu is a term that comes from the representation theory of S1. This would come from the representation theory of S1, which is trivial. So somehow these parameters easy to control. So if you have any correlator with any kind of expression, then you could have L classes or anything, and you can differentiate. Then that's equivalent to a certain yeah. Second property is that just like in Brown-Witten theory, we can use the sample product to find two differential equations, and then this S matrix gives you a solution. Namely, 2 minus 1 yes Q1A is equal to the proof function from A. So you think of this as a linear operator in the logical function multiplication. Okay. This is a product of a matrix. And then we also define a J function. The J function is 1 minus 2 1 1 once 1 point 3 alpha. Or 8. You are very answer. This is two thinking like I don't want to make sure this 1 minus right? And then that 1 minus QE. Yes, thanks for So then, so this is just a definition. So then what is true is that this J mu Q is literally the first form of S inverse.
Great. What?
In order to get to quantum homology, first you have to set all these equivariant parameters to 0. You have to rescale the non-equal variables by some power q minus 1 appropriately, and then pass to the limit when q is 1. Then it will become the same one.
Quantum cosmology, you don't deform the one fact there.
Yes, this is, you can do the same thing in the cohomological ground theory, but this correlator would be 0. Somehow by accident, zeros. So, but this is also related to Smith was talking yesterday. So you can see here that if you start differentiating with these parameters, new A, thanks to the second equation, right? You see that you generate the entire S matrix. So somehow this is some kind of a primitive element that you differentiate, you get the entire information. Okay, and now I want to, until the end of my talk, I want to tell you two theorems. First, I want to state how you can recover the entire Genus-0 theory from this matrix. Okay? And then I want to show you, in the case of a point, how you can compute this function. Yes. So this stability of frequency is 1 minus 1 minus. Yes. So then, but you see, it's this is S and J is related to S inverse. It's not quite, and no mistake. There's no mistake. This is using the string equation. Okay. But now, how do we recover the invariant from this matrix? This is done with the simple principle. Let me try to write a generating function for all Genus-0 invariants. So I want to introduce some formal parameters of all invariants. So here k is greater or equal than 0, a is between 1 and n. Here sequence formal variables, and I want to use the following series as an insertion in my correlate. So it takes sum over both k and a, then k a, well minus 1 to the square. And then, well, the Genus-0 invariants can be organized in the following way. So I already must know. They will depend on if I'm going to exclude mu1 from my formula because in some sense this mu1 could be identified with 0. First proper. Anyways, so this generating series is the following. So you take sum over all n from 0 to infinity, a from 1 to n, and then we simply the following is so p alpha a divided by n factorial, then 1 a, and here I'm going to insert TL. L. 0 equals 10. And this will depend, the first parameter, which is u1, I'm going to set it to 0. And then the rest I will. And this takes values in the tagging of text. And otherwise, it's a formal series here. Then these variables P, Q, and the knowledge variable. And so if you expand this as a power series in these variables, then the coefficients are exactly the invariants that you want. And now the main is that we have a differential equations in these T variables that allow us to compute the difference. So there is a small trick. So first, we have to solve the following equation. So let's write the J function. Right? In the J function, I'm going to put Q to be 0. This is the Q slope. Right? And I will this to be 1 plus number. One is this. It can almost in K, but it's a formal power series in KGW. Right? In your 3 and then we solve it for u1. So then you can solve for mu1 in terms of some formal power series in T and the remaining parameters. So this is going to take values in the KD, right? Within the T, if we have the following differential equation, u and a is equal to minus 0 when q goes to infinity, q minus 1 to n, controlled by s of u like so here I want to assume that phi1 is the unit in the molecular AD, and then this is the derivation direction of the unit. And by S means that we want to take S Q, and we are going to replace Q1 in this solution. And that gives us so this system tells us how the generating function of theoretic group invariance depends on T. In particular, if you computing for T equals 0, then in principle this equation can. And I need to say that this is not a difficult result. This is essentially equivalent to WDV equation, more or less. It means that you don't have any insertion. And then this kind of correlator is already contained in the estimate, in the general. Okay, so in the remaining 20 minutes or so, I want to show you how you can compute the J function in the case of a point. And this computation was done first by given tau using Rambus description of M0n bar. So there is a description in terms of blow-ups of okay, but I want to show you a different proof. So here this consider this is considered the so-called universal matrix one. This matrix is you forget the one smart point and you contract all unstable components. There's some sections right? And it is known that so this is some kind of a tautological vibration, which is it has the following form. So if you let's pick a point in M0n bar. So this means some rational n mark point. Let's say this is guy. Then the problem is that the fiber over this is actually isomorphic. So what is the isomorphism? So for example, if I take a point here, so I need to construct an isomorphism between this curve and the fiber. So if I choose a point here, then I have to construct for you a rational curve with n plus 1 mark points. Right? So if I pick a point which is not a mark point, then it's clear, it's what we expect. So it will be just, you just take the n plus. Where is this? And this would be the n plus first. You know, if you what do you do when you have this kind of rational curve with n plus 1 points you associate with this point? And then what you do is you take this your original curve. It's a giant position. So here it is. When it's supposed to be the mark point, you just add a copy of P1 with 2 more mark points. One is total. The other one is central. So this way, the entire fiber over this curve is actually isomorphic to this curve itself. I want to use the following fact. So this line bounded Ln plus 1 that I briefly mentioned before actually is the same as you take the relative dualizing shear twisted by the device of P1 plus Pn. So here the section Pi is the one that this point it associates this. This is the X. Okay. And now what we want to do is we want to consider so this line bundle will define a map from M0 n plus 1 to a projective space. So this line bundle defines map from M0 n plus 1. And actually you can see that the projective space is Pn minus 2. Yes, it is orange. Which is contained in P n minus 1. And so let me try to explain. We can write it actually. I think there is a very nice formula that I want to explain. So let me denote continuous coordinate n minus 1 n. So then the image of our map is going to be into the hyperplane. Say 1 plus sin into 0. So, yes. So the question that I want to answer is: suppose that I give you some rational curve with 10 mark points. What are these coordinates? Psi 1 and psi n. Right? This is a problem that I believe everyone solve, because just think that you is bounded to the final, this curve. You obtain the canonical default twisted at this and devices. So you want to consider the homomorphic method. And the answer is the following. So I want to find the map. Which carries the n plus first. Then the remaining mark points, some of them are going to be on this component. I denote them with pi, and then the remaining mark point will be on other irreducible components. So there will be some nodal point Q1 and etc. To L. Yes, and so the remaining mark point would be Pj to J1, some Pj with JL to JL. And then we do the following. So let us fix an isomorphism. This is 0 P1. And we fix it in the following two conditions. First, I want Pn plus 1 to go to infinity. And second, if you fix this the infinity, then the choice of this isomorphism, there is some affine group of transformations left. So using the translation, you can arrange that this sum is 0. Zero. And finally, there is some rescaling left, but we are defining a map to projective space, so that doesn't matter. And then the map then the homogeneous coordinates become the following. So psi I is equal to pi if I belongs to I. And it's equal to pk if I belongs to k. So using this description, you can see that fiber over psi is not a form. This is if and only if you can change pairwise distinct IJ. Such that psi I equals psi j equals psi k. So this is another complex coordination space here minus 2. And outside of this is going to be isomorphism. So as Alexei said, this is actually this Pn plus 1 is the rational evolution. N minus 2. And then it follows that the higher direct limit is of 0. This is the theorem from functional singularity. This is the theorem that you have to prove to define the rational singularities. With Hessian algebraic tonality, and you take the resolution, usually the third direct is of 0. This probability will be for all other resolution. And in this case, we can take the resolution just here minus 2. And 0n goes that. Okay. So now we are in position to compute the invariants. So let us look. I did this with the n plus first mark point, but here you can choose any other mark point and do the first. Okay. So let us look in our case. Let us look into this construction with n0 n plus 1, and I'm going to use the L1. So I will note this matrix 1. And this is a length n minus 2. This is the equation method. Okay. So now, if you want to compute the J function, then you have to compute the push forward of L1 to the any power L. So, definition, this is some k from 2 to infinity. Then you have to take the push forward of L1 here. Okay. This L1 to the n is 2 matrix of 1 or n. Because we constructed this map using 1 L1, which means that more formulas must be the full map. So therefore, we can conclude that this is this push forward is just some equal to infinity. Then we change 0. Oh, okay. And this space here is exactly the symmetric c to the k minus 1. Where what is this c to the k minus? Well, we have the following exact sequence. Patients of the state. Here the coordinate x is mapped to x1. Here is mapped to the sum. Okay, so this is the trivial representation. Let's make it pregnant. And then, therefore, we can put that the symmetric part of c to the k is just the sum 0 to n symmetric power c to the k minus 1. Remember, this space that we want, this representation of SK that we is just a difference. K minus 1 is just the difference of M of K and M minus. If you want to compute J function, well, if you substitute this formula for sim m k minus 1 here, then
Sorry, this equality. Yeah.
in the representation, I input this k. But so you substitute now this into the definition of a J function, and you find that this is exactly 1 minus q. And here we have to compute some series which has the form some some due to and here. I can think of uses so to express this equation. The presentation is still the same. This is done using the size effect. This formula for the derivative. You see this, so this c to the k could be decomposed as rectangle c k minus some. So you think in terms of the basis vector, basis consisting of a standard basis vectors, these are the first R bases. These are the last k minus R. So this is some S R minus S k minus R variable. And therefore, we can write the k of the direct sum. Then this becomes sim m prime. We are things of k minus R for m second. So the symmetric product will be composed of the direct sum such issues. And now, if you remember the formula for the derivative, we want to compute the trace with respect to 1 to R. Now one can check that the trace of 1 to R from this representation. This is 1 if R divides M. And 0. Therefore, now if we try to differentiate here, suppose now that we want to compute this derivative. It means that I have to, according to the formula that I gave you, I have to restrict this to a representation of SR, SK minus R, and then compute this trace. And we see from here that what would be left is from A from R to infinity, sum L from 0 to infinity. Then this would be, I will decompose 2m as m second plus the multiple of R, right? And this would be Q second. Let's see, A minus 1. After you apply this formula for derivative that I gave you earlier, see that the derivative of this series becomes this, and now you can recognize that this if we pull out Q to the LR, right, and sum over all x complement, right? So you're taking exactly 1 divided by 1 minus 2 to the R times f of u. And therefore, the conclusion is that f of u is exponential of sum r from 1 to infinity, 2r divided by r squared, 1 minus yeah. And that gives us a formula for the J. Thank you very much.
Or any question.
So the ordinary K-theoretic ground frequency theory is when you put all these parameters near two. For new one also, two there's new one somehow is part of the old theory, you know. I think that this point this permutation invariant. In some sense, it is you have to study it if you want to understand the ordinate. Because if you try to compute the non-permutation equivariant Gromov-Witten invariants using fixed point localization, then you have to work with some Kawasaki Riemann-Roch formulas, some Lefschetz space formulas, and they naturally lead to this kind of correlation. You have to understand permutation equivariant. And also there are some computations in the J function. If you have some variety which is a hypersurface, let's say in a projective space, and then you can start with the ordinary K-theoretic J function of the projective space and use some kind of quantum Lefschetz principle to compute. There's some formula that you expect that there will be the J function of the hypersurface, but they are not. They are actually of the permutation equivariant. So this is the second reason you have to.
And let's